Thank you so much for the introduction, Leah, and to you and Lydia and Angela and everyone at NCCEH for the invitation to be here. I think of myself as a public health engineer, and so I'm so pleased to be connected to you and to your colleagues and stakeholders of the NCCEH. So let's go ahead and get started. So I'd like to go ahead and share my screen and talk today about climate change exacerbated landscape disturbances and the effects they can have on drinking water treatability and what we as public health folks can do to hopefully manage some of these threats. So I'll go ahead and share my screen. Hopefully you can see it. And I'll go ahead and project. So I thought I would start off as I'm getting this going a little bit with a background of how I ended up here. So we know, all of us know, that landscape disturbances are occurring in a warmer world. All you have to do is read the news, turn on the TV to see this. There's fires, there's floods, hurricanes, and they're affecting the landscape. Here I've got images of the wildland landscape, but also urbanized landscapes as well. And inevitably, those disturbances mean impacts to our source waters. Now, today's talk will have a very Canadian focus. But really that focus is much broader beyond Canada, because it starts with, when you have large landscapes, where does your water come from? And what might the impacts of climate exacerbated disturbances be on those landscapes? So for us in Canada and many people across the world, even if you don't live in the forest, often a lot of your water originates in the forest. But really this discussion goes beyond forests, because it's really about the impacts of disturbances on wildland interfaces and then on urban interfaces. And we're going to start with wildland interfaces. So like the forested landscapes, where easily at least 60, probably far more than 2/3 of Canadians, their water originates, may not all come from, but a lot of it does originate in forested landscapes, and certainly natural landscapes. So why am I here? I am a traditionally trained engineer in environmental engineering and chemical engineering. I did a lot of my research as a PhD student on treatment process optimization. I worked specifically on, amongst our most paramount objectives of drinking water treatment, which is pathogen risks, because they're acute risks. And some time ago, around 2004, 2005, I got asked to come and look at a wildfire in Alberta, southwestern Alberta. And really for me, that was a transformative experience, because I went from treatment optimization to really starting to think more about, my job isn't just about water that comes out of a pipe and the contaminants that may or may not be present in it, but there's a relationship to the source, to the landscape, and there's also a very real relationship to health risk. And so my career has evolved over the last now 15 years or so into not only treatment optimization, but source water protection, risk assessment, and really trying to argue for those connections, because more than ever, climate change is throwing out the door all of our traditional ways of managing these risks. And perhaps throwing out the door is not a fair statement. A better statement is we have to do more. And it's something that we can't avoid. And part of my goal for today is to really focus in using fire and years of fire research, and then moving beyond fire and how it's connected to other risks. Really focusing and saying, what can we do? What can we do as advocates for health protection and the linkage between public health and what happens in the environment? So like I said, I've worked on fires. I thought I started in 2004 on the Lost Creek fire and it would be a one-off, but the fires kept happening. And then after fires, there's usually mudslides, erosion events. So lots of disturbances that become compounded on the landscapes. So what do? It's amazing how our industry has evolved to now, in the last 4 or 5 years, I've been leading a pan-Canadian internationally partnered effort called For Water, which is all about forested drinking water source protection technologies and literally managing the landscape, leveraging and integrating green infrastructure to develop techno-ecological nature-based solutions to manage threats to water. The idea is healthy forests provide healthy water, and we need to manage them because climate change has really pushed us into a space that we're losing our forests, we're affecting the landscape at a far greater rate than we ever have before. So that's where we're at now. And so the question is, well, how did we get here? What are these connections? And so in the introduction, Leah mentioned that our work started pretty innocuously in this regard. And some of the main messages of that work were, look, climate change threatens drinking water security in a lot of ways. But one of the key ways is one that people don't think about. People often think about drought, insufficient water supply, and all of the problems that very, very truthfully and realistically can cause. But climate change can also change water quality. And threats to water quality can also be threats to public health, because there is inequality across the world and even across the country with respect to public health protection and how it is tied in to the provision of safe water. And this is where one of the key messages I hope that comes across to the health community is the following. Yes, contaminants of health concern are significant. We have to worry about pathogens. They're the paramount objective of drinking water treatment, is their management. And yes, there are more chronic risks we have to worry about too. But one aspect of water that we do not advocate sufficiently for is the ability to treat it, and the ability to treat it cost effectively in absence of needing 3 years of upgrades in a community that's waiting for safe drinking water. So treatability is important too. And that was a big part of our discussion in 2011 when we were looking at the effects of wildfires, because wildland fires, fires that occur predominantly in forested areas where you don't have much urbanization, really start to threaten water quality and treatability. And there's a cost to treatment, and it does not scale proportionally for per capita. Smaller communities pay more for treatment per person than larger communities do, because treatment is a step function. The more your water quality is challenging to treat, and notice I didn't say is contaminated or deteriorated, the more it is challenging to treat, the more your treatment costs. And one of the big realizations that has come in the last 10 years or so from the water industry more broadly is a recognition that we need to do more with source water protection, that reliance on technology in plants, simply having technology is insufficient. Simply having this gray plant infrastructure is insufficient, that we really need to utilize our green infrastructure, our source watersheds, so that we can successfully have a chance at managing risks from changing climate. Because some of these disturbances can be catastrophic. And I'm going to talk a little bit about why this is so important, because it is really some of these traditional regulatory perspectives that really handcuff us with respect to taking on some of these challenges. And what is really dire here, and this is the only part of the talk where I want to be dire, but if you read the IPCC report from 2022, the most recent one, what it emphasizes is that we already know that these challenges can exist with climate change. But what we're just beginning to think about and realize is that compound disturbances, so multiple disturbances back to back, can really derail us. If we keep burning forests and we don't have enough time for recovery for that growth to come back, we may not be able to get back to that same place that we appreciated with respect to forest structure and function. And so that's one example, but really that is true for all of the landscape. And this is where we need to be thinking. And so that connection between the landscape and water supply and the things that we know about as public health professionals becomes all the more urgent. And so let's remind ourselves of what we know about water treatment and its relationship to public health. in its simplest form, as it evolved, and we've all heard these stories about what happened at the turn of the century in the 1900s and the recognition of the importance of basic hygiene. Historically, water treatment, and this is surface water treatment here, has focused on removal of whatever we need to remove up front so that we can efficiently disinfect the water to protect people from waterborne disease. And so historically, we removed whatever we needed to so that we could disinfect well. Now, over time, we've learned that there are other contaminants, including chemicals that pose chronic risks. But the paramount objective has always been pathogens, and will be pathogens because we're talking about immediate or acute risks. Now, with the evolution of our understanding of the relationship of water and health, we've learned that there might be other challenges, such as those posed by algae, for example, and they can produce toxins, so those also are acute risks. And as our water supplies deteriorate, we've learned that with managing especially chemical risks, we often have to invest in advanced treatment technologies such as membranes or advanced oxidation processes, et cetera. But let's not forget, while all of the research, or most of the research, has focused on downstream treatment, it's all contingent upon our capacity to remove solids and organics. Natural organic matter drives coagulant dosing. These are the basics of treatment that go back to the 1930s. But if you think about changing climate, more than ever, these are critical. And why are they critical? Because if we can't produce sufficient amounts of safe drinking water, if we start to threaten the availability of that water and we don't have the capacity for basic hygiene maintenance, infectious disease spreads and people will die. So our primary priority is to keep water running and then hopefully make sure that it's safe and potable. First running, then potable, and then sufficient amounts. So we deal with the acute risks first and then the chronic risks. So this is the landscape against which we work. Okay. So let's remember how to prioritize this, and let's think about how we do that in a changing climate. So the part that is always, I think, amazing, some people say stunning, but I say amazing. It is amazing how many of the challenges that we face, if we go back a couple of slides, when we try to implement this multi-step, complicated, technically advanced process of water treatment. It is amazing that we can really get most of the way there by choosing a few parameters or looking after a few parameters. And those can be simplified down to solids and organics, predominantly natural organics, but we usually measure dissolved organic carbon. So you can have synthetic organics in there. And yes, for synthetic compounds, we need advanced treatment. So, which is why we look for them. But in absence of anthropogenic contaminants, which climate change itself does not deliver through these disturbances, it's only when they occur on anthropogenically impacted landscapes that we see anthropogenic contaminants. We're largely talking about natural contaminants, if you will, that don't have necessarily a health impact themselves, but their health impact comes when we can't produce water. So we talk about treatability. So drinking water treatability has to be considered. And anybody who gets into the design and operation of treatment systems knows that the next thing we have to advocate for is it is not about, do you have the right technology? We have the right technology to make safe drinking water on the space station. We can treat most water. The question is, how much are we willing to pay for it? And really, that payment isn't just about buying the technology, but it's about operating it and maintaining it and recognizing that in some jurisdictions, in remote areas, some of the supplies we need are really difficult to bring in. So we need to get past, do you have the right widget? And talk about, can we reasonably operate the widgets we have, whether they're green or gray or some combination therein. That is the only way we're going to deal with climate change and water security and health. Why? Because water can be challenging to treat, and we've forgotten that. Water is especially challenging to treat when it fluctuates. Give me a super contaminated water supply, we can treat it. Again, how much are you willing to pay for it? The challenge comes in when it's fluctuating. And that's where storms, fires, hurricanes, that's what they give us. And so the analogy that I often talk about is, how many spring freshets does one utility want to experience where they have these huge swings in water quality, and we don't have the telemetry, the sensors to be optimizing treatment in real time? That's where the backups occur. That's where the failures occur. It's not because we don't have the right technology for treatment. Sometimes it might be that we're inundated, but most frequently it's that we have a backup, we don't have the right sensors, we overdose, and then there's a domino effect. And there's nobody who can say that the probability of being responsive and rapid in response and having all the right sensors is going to be greater in a rural, remote, or marginalized community. The challenges are different because the resources are different. And without a doubt, that is from where the inequalities come. So to kind of get through the motivation, let's talk about, well, what do we see? Because disturbances, watershed disturbances have effects on water, and water quality deterioration or fluctuation can be expected. And so the question is, what do we do about it? I've presented these slides before and presented them to NCEH, but they're powerful. This is sediments, turbidity, from reference burned and post-fire salvage logged catchments over a period of 4 years. So green is reference, and there's progressively more disturbance. And our glaciated Canadian landscape is very rich with sediments because the glaciers ground up our landscape. And it is amazing when you go back and forth. If we had studied this fire for a few years, we would have thought there was recovery in our system. But in fact, we see that these impacts can persist for decades. Not only do we see it with sediment, but we see it with nutrients that can cause algal blooms that can clog up our treatment processes. Same notations here, not all of the nutrients. The nitrogen seems to taper down, but it's not surprising that phosphorus doesn't, because phosphorus is transported with sediment. So when we talk about internal loads in reservoirs of nutrients that promote algal proliferation, this is what we're talking about. And you go from something like what's at the top of this slide to something more like what's at the bottom of this slide. And not surprisingly, the inputs and the shifts in water quality are often linked to higher flow conditions. In some cases, those are really easy to predict, but in places like the Boreal, Northern Ontario, Northern Alberta, for example, Fort McMurray, it's really difficult to link the landscape to the water supply because the hydrology is very complicated. So it's very difficult to predict and anticipate when these fluctuations are going to occur, and they can occur quite rapidly. And we see that they have this history over a long period of time. I've got the references with each of these slides that kind of link to the more detailed stories, but I'm trying to get it to the end point in about 40 minutes of what we can do about it, and speak to these contaminants that are not contaminants of health concern, but can have tremendous health impacts if they're not managed. And so when we look at some of these disturbances, it is these disturbances, it's the turbidity and the carbon and the phosphorus that's associated with the turbidity, the nutrients, that lead to biostabilization of our water supplies. And you'd say, okay, well, if you have biostabilization, what does that mean? It means we have these biofilms, we have these nutrient-rich sediments, and then we have these biofilms that appear because of the nutrient availability, and they kind of glue everything down to the riverbeds. And you say, okay, you might have some reduced groundwater yields, but in terms of water quality, isn't that a good thing? The turbidity is glued down to the riverbed, so to speak? And the answer is, well, no, because first of all, there's two things that happen. You're going to have this biological activity, and in association with it, we've seen increases in taste and odor compounds, the potential for toxin formation. But we also see that when we have more energy in these systems, so a burned versus unburned system here, when there's more energy in the system, yes, it takes more energy to to basically scour those riverbeds. But when we do, so the first column or the middle column here is the energy requirement. When those storms do come in, my goodness, do they take more material with them? And so what does that mean? Flashier, harder water to treat, and less predictability in these systems. So a key message that we can advocate is the importance of being able to treat the water, not because you have the right technology, but because you're operationally supported, telemetry, trained operators who practice. And even then, we still don't get it sometimes because it's challenging. And what this figure shows, I think, is really powerful as we talk about our wildland landscapes. And fire, again, is assertive. Fire is really hard on water. But disturbances like hurricanes, where you still have increased erosion, they're going to have the same, or not exactly the same. They're going to have similar impacts. They're going to have the same threats for treatability, but the magnitude of those impacts and the frequency might be different. But they're the same considerations. And what you see here now is we've got an unburned system. We've got a flood after a fire in the blue here. And then we've got an unburned system again and a wildfire. And then we've got logged systems down here to the right of each of these. And we have sediment or turbidity, phosphorus, which comes in conjunction with that sediment, especially the fine sediment, not the big sediment that we manage reservoirs so that they don't fill up. I'm talking about something that might comprise less than 5% of the solids mass, sometimes less than 1%. This is colloidal, 1 micron, 20 micron size particles. This is not what you worry about filling up a reservoir. A different type of sediment our industry doesn't frequently talk about. So those two come together. And yes, the carbon originates on the landscape too. It's particulate. But then when it makes its way into the water supply, it goes through a dissolution process. So what we see here is that fires and floods punch well above their weight class with respect to having potential impacts. This is all in southwestern Alberta in a series of compared catchments. Does this mean that anthropogenic disturbances have no impact or are always less severe than the climate-exacerbated disturbances? Absolutely not. If you don't have treatment for a specific contaminant and you have a spill because there's a release of a synthetic organic, of course that's an issue for the water supply. But just as big of an issue, and one that we don't talk about as much, is the wildland natural fluctuations in water quality that prevent us from being able to treat water with existing infrastructure. And so we need to think about these risks. And as I've pointed out before, solids and carbon need to be managed, but it's also the solid associated other nutrients like phosphorus. And so we need to start thinking about and adding to our repertoire of water quality metrics. We need to also think about nutrients like phosphorus, and we need to think about immediate versus long-term risks. So the carbon, the coagulation will be some of the immediate risks, but what about longer-term risks? And those longer-term risks really are linked into this biological activity and the proliferation of cyanobacteria and other algae. So this is a really interesting study, and it's a critical study that I wanted to share that came out of the United States that focused on this is a continental-scale evaluation of well over 1,000 lakes, reservoirs, streams, rivers. And the net message here is a very simple one. You see 2004, 2009, and 2014. And what you see here is the percentage of systems with a very low level of phosphorus availability. If you have a lot of phosphorus available, it's a eutrophic system because it's indicative of nutrient, it's a nutrient and it's indicative of broader nutrient presence. So what you see for streams and lakes is in both cases, they're going down and they're going down significantly. And if you look at the bottom corner here, what they're saying is that there is across the board ubiquitous evidence that eutrophication is happening. And so you say, okay, well, why might that be? Is it because of what's going on the natural landscape? And the net result is It's climate change exacerbated landscape disturbances that are significant contributors in forested catchments. I think the wording they use there is places where we don't have point sources or non-point sources that are typically understood, underdeveloped catchments. So one of the pieces of work that was recently done in southwestern Alberta was trying to parse out what happens in a community as we go downstream and look at cumulative watershed effects, which are notoriously difficult to decouple. But one of the sites, site 4 in here, was after a wildfire. And without going into all of the details of the story, what I wanted to point out is that this study provides direct evidence of what was speculated about in the other study, which is in this study, you can see that if you parse the system up into upstream and downstream, and you look at phosphorus here in the bottom left corner, and different fractions of phosphorus, some of which are more bioavailable than others, you really start to see that there's more appearance of phosphorus and bioavailable phosphorus after the wildfire impacts make their way into the main stem of the river. And you see these shifts here as well. And you can see that that phosphorus is associated with turbidity, with the different types of turbidity, the different minerals that are known to absorb phosphorus. Why is this important? This is important because it provides direct evidence of how these impacts are occurring mechanistically. It's erosion. It's fine sediments, not the big gravels. It's the fine sediments that we do not normally manage in the water industry. And we think about high quality systems having to lose so much to lose, but it's also, and the most to lose, and maybe if they don't have enough treatment. But Fort McMurray has taught us that impacts can be observed in all systems. Everybody's familiar with the wildfire that occurred on top of the city of Fort McMurray. And what we saw there was jarring, because we saw that, yeah, there were some watershed scale impacts. Some people thought there wouldn't be any at all because the river already it's deteriorated already naturally. But what we saw is, in fact, this can happen. A small fraction of the landscape, less than 6%, can affect water supply and treatment directly. And it has continued to do so for a prolonged period of time because of these plumes that make their way out of the watershed. And what we've seen in Fort McMurray, you might have, if you read in the news, is increased costs for coagulation, short term, or immediate term, I should say, the impacts we saw immediately in association with shifts in carbon, the main driver of coagulant dosing needs. But we also saw these algal blooms in association with elevated, past a tipping point, phosphorus associated with fine sediments that are colloidal in nature. And we've seen them every year, and we've seen shifts in this system. And what we found is not only are these blooms occurring, we speciated them, they keep coming back, and they have the potential to form toxin. They have the equipment. We haven't found toxin, they haven't formed it, but they have the equipment, the genetic equipment to do it. Long-term risk. What drives an algal bloom? It's something that makes it initiate. We don't know. What initiates toxin formation? We don't know, but the risk is now profoundly elevated, because when we're talking about toxins, these are real risks. These are not hypothetical or potential. These are neurotoxins, these are liver toxins, and if they're present at high enough concentrations, they can have very significant health consequences. This is probably the biggest threat to the provision of safe drinking water, is toxin formation. Most utilities are not equipped to deal with toxins because advanced treatment is necessary for the treatment of toxins. And so now we start to get into what is our best bet for treatment of toxins? Ozonation. As you can see here, it deals with most of the toxins that we know of that can be significant. And in combination with chlorination, we can really hit most of them. But you only build ozonation if you have to. So the community of Fort McMurray, currently a community of 60,000, is looking at potential costs ranging from 20 million to probably in excess of 60 million because of these challenges. And so what can we do? Well, it depends on the type of system. Some of the work, one of our grad students by the name of Emma Blackburn has done is really focusing on this concept of green technology and green versus gray infrastructure, and trying to look at what are nature-based solutions. A lot of people confuse green technology and nature-based solutions, but what I'd like to propose here, and what Emma's proposed, is that how green something is going to be relative. And when we start to talk about various solutions that are green, we need to parse out green and nature-based or natural resource-based from other types of green. Green technology certainly can be natural resource-based or nature-based, but it can also simply be green because it's less energy intensive or produces less waste, or in many cases utilizes a much smaller footprint. And one of the big reminders about green technology, of course, is that it still has to be fit for purpose and provide what we need with respect to treatment. And so it necessarily becomes relative and case specific. It's always a comparative, and you're looking at a spectrum. And one of the things I'd like to say about nature-based solutions is that when we get into the domain of public health protection, the notion of relying exclusively on nature is a pipe dream, because we need to make sure that the water that we treat is sufficiently safe for distribution. So necessarily, we're talking about techno-ecological nature-based solutions. And so the question is, for many people who talk about nature-based solutions, it's how much of that natural resource basis can we bring into play? And in some cases, it's a fair amount, but in other cases, perhaps much less so. It depends on the nature of the contaminants. And so one of the other messages I hope here that we can agree on as public health professionals is really, when we talk about nature-based, really let's talk about the range of green, because at the end of the day, we need to be able to implement these technologies and make sure they're working effectively. If they happen to be natural resource-based, if that's what a community values, great. But know that that's not the only way to be green, and know that you can't be exclusively nature-based when it comes to safe drinking water. And so we can start to talk about how can we look at green technologies and nature-based solutions. And one of the things that we start to see is that when you look at various types of treatment technologies, high rate clarifiers like what they use in Calgary post-flood, the ActiFlow system, a little bit less control, like a biofiltration plant that relies on slow sand filtration, riverbank filtration. There's a spectrum. And what we see with green technologies frequently is what we're trading off is control. We always in design talk about the more moving parts you have, the more control over your system you can have. And so one of the discussions we're having is, what about nature-based technologies and the extent of control? One of the pieces of work that Emma did was she looked at biofiltration technologies. And I just want to go through this briefly. She looked at adding wildfire ash to water to look at just dealing with that carbon threat. And she looked at biofilters and duplicate, and the long and short of what she did was she had a control with no wildfire ash, but still biologically active, a little bit of ash, a little bit more ash, and then even more ash. And the long and short, without getting into all of the nitty-gritty details in her, I think, over 150-day experiment, because we had to acclimate the filters first, was that, boy, could these filters mimic the control filters. So they were resilient to these significant additions of post-fire carbon into the system, which is fantastic, because that's the origin of some of the threats. And this is without coagulation in the system. So that was wonderful. But what we also saw is that biofiltration is not a silver bullet, because some of the shifts, while we could remove the biodegradable fractions, so you can see here, there's an equal level in the control of these low molecular weight neutrals that are biodegradable from the influent to the effluent. From the influent to the effluent here, we could remove those. But in other places, for example, the humic substances, those were quite recalcitrant because they're not so biodegradable. So biofiltration offers resilience, but it's not a silver bullet. It depends on the nature of the carbon. The last thing I'll quickly point out here, because I'm almost at my 40 minutes, is another type of green technology or techno-ecological nature-based solution, and it has to do with the landscape. Another significant opportunity that we have and that we haven't fully embraced as an industry is the notion of source water protection. And I think this is where public health experts, regardless of the branch of public health you're in, can really rally and talk about how much progress we've made historically with source water protection. We protect our water supplies so that they're not contaminated. That has really served us well since 1980, which was the year of water, where we really started in that time to recognize, especially with anthropogenic chemicals, the earlier publication of Rachel Carson's Silent Spring, that my goodness, if we dump things into our water supplies, that will affect our health, even in the subsurface. So that has served us well. But we need to continue to evolve and grow. Putting a fence around our water supplies, whether it's a real one or simply a regulatory one, is insufficient because Mother Nature doesn't care about that fence. Mother Nature, a fire is going to go past that fence. And so the question is our landscape, whether it's anthropogenic, impacted or wildland, it's going to be impacted by disturbance. And so these notions of source water protection necessarily have to move and evolve toward landscape management with an eye to protecting actively our water supplies and moving from, again, sort of a Mother Nature knows all, because Mother Nature will do very well. The problem is the recovery period post-fire in Western Canada could be 120 years, could be 100 years. Usually we want things to bounce back more quickly, or we want them to be resilient or resistant to those disturbances. So we can help Mother Nature. I'm not suggesting that what we've got in front of us is necessarily the way to do it, but there are forest management techniques that include some sort of thinning, silvicultural practices where we look at species diversity and resilience to all sorts of disturbances. That's how we're going to hedge our bets with respect to protecting our water supplies. Those are inextricably linked. And it's really important that we go all the way from the forests to the health protection aspects, because that is one way in which smaller communities will better be able to afford provision of safe water, because these landscapes serve much more than one small community, whereas the treatment technology in the plant serves that one small community. And what's the one thing we can advocate for more so than anything is controlling disturbance effects. We all want paper. We all want wood for our homes. We all want to maybe not fireproof our forests, but make them more resistant or resilient. So they either resist fire or they bounce back from fire more quickly. The way to get at it is by managing erosion, because if these materials don't make their way from the landscape to our water supplies, they won't be there to challenge treatment. So there was a study we did collaboratively led by Aldous Sillins and colleagues from the University of Alberta. But the long and short was, regardless of the type of disturbance on the landscape associated with forest harvesting, and you can be doing that to increase the resilience of the forest. If you look at the carbon, we didn't see any net impacts. And even years after the fire, after the disturbance, we didn't see net impacts to the water supply. So yes, we can make our forests more resistant and resilient to these disturbances, whether it be disturbances from logging or disturbances from Mother Nature. And that will help protect drinking water treatability. So I think I'm about at time, and I'm happy to elaborate on any of these topics, but I just wanted to say that what are key considerations if we want to distill things down, especially for rural, remote, marginalized communities that often have and comprise small drinking water systems or private systems, is that climate change exacerbated threats from the to the landscape and their effects on drinking water treatability can be greater than anthropogenic threats. Not necessarily, but they can be, depending on the extent of treatment available and, of course, the extent of the disturbance, but they certainly can be. And we need to act on what we know, which is, at the end of the day, source water monitoring is critical. A lot of people look at turbidity, We really need to look at carbon, and we probably also really need to look at nutrients like phosphorus, not just in the water column, but in the solid phase, in the fine solids, because that's how we can start to gauge shifts in our system and start to gauge how much of that risk our system can absorb, because it's so important. And then we need to look at technology and look at not only do we have the right infrastructure in the plant, but can we maintain it? Can our operators longer term maintain it? We can look at biological treatment, and this is one of the points I didn't make, and so I'm going to make it now, which is this notion of biological treatment doesn't require as much control. If you live in a region where it's difficult to maintain constant supervision, multiple operators at a utility, biological technologies may offer resilience because they require less operational control. And that is something we definitely need to explore more. And then finally, if we really want to protect public health, especially for smaller communities, we need to start engaging in discussions about actively managing our watersheds so that we don't have the extent of treatment risks that we might otherwise see from some of these climate exacerbated disturbances. So on that note, I'm happy, this is a lot to cram in to 45 minutes or so, so I'm happy to answer any questions or respond to any comments. I'd like to acknowledge a lot of our collaborators that support this extent of research on the landscape and in plants, and I'd be happy to answer any questions or respond to comments.